just going to give a brief introduction, talking about 4 different areas of machine learning. Then I'm going to go into detail for one particular area. I'm going to spend a fair amount of time on linear regression with many regressors and look at lasso and related methods. Then I'm going to continue with methods on supervised, with other methods for supervised learning, namely the regression trees and various variants on that. I'll briefly mention another set of methods referred to as neural networks and sometimes as deep learning. And I'll talk a little bit about methods for combining various supervised learning methods. And then in the last part, I'll talk, and that's going to be fairly brief, about some unsupervised learning methods. But so, by general introduction, I'm very glad to be here. I gave some of these lectures with Jeff Wooldridge in 2007 when Marty Feldstein started this series. At that point, we didn't really do anything on these methods. And if I look back at the topics we covered then, it's not so much that we covered stuff that wasn't relevant, but this is really the biggest area in terms of what I now cover in my graduate econometrics courses that wasn't covered in those lectures. And so what I'll try to do is sort of give somewhat of an overview. It's going to be partly very short and condensed. There's a lot of courses, full semester-length courses that deal in depth with these topics. But I want to give people a sense of which methods may be useful ultimately. And some of that isn't going to be that these methods are sort of immediately useful, because it's partly going to require a paradigm shift where the way we traditionally do things in econometrics sort of imposes a lot of discipline and structure on the way we approach problems, and a lot of these methods don't really fit into this framework. But being familiar with what these methods can do, I think it's going to help make them useful in economics. So then this, and this is sort of partly echoing what Susan was saying. A lot of these machine learning methods are much more about the algorithms than about asymptotic properties. And so there's no unified framework where often in econometrics we write down models, and then we know where to look for methods for actually implementing these models. We may use maximum likelihood estimation. We have a lot of results on what the properties are there. We know in many cases these methods are going to be consistent, they're going to be efficient, they're asymptotically normal, and none of these things come up very early on in the discussion of these machine learning methods. The question is typically much more whether it works in practice, which is obviously a very nebulous concept, rather than what its formal properties are. And as a result, there's sort of a proliferation of methods and algorithms, and there's not always a lot of discipline in choosing between these methods, and at the same time, that's very liberating in the sense that there's a lot of room for coming up with different methods, but it makes it hard to figure out which of these methods work. And again, in contrast, in large parts of econometrics as well as in large parts of statistics, there's a very well-defined structure for doing things. We look at, for example, we look at p-values, and we decide things are significant if p-value is less than 0.05. So very interesting that in other fields there's a lot of pushback there as well. There's a psychology journal that's just decided they don't allow the publication of p-values anymore. And sort of partly in response, the American Statistical Association has set up a committee with the somewhat odd task of coming up with a statement about the proper use of p-values. I've been on this committee, and it's been very interesting, partly because there's sort of clearly no consensus on how they should be used. But at the same time, in these machine learning methods, there's very little of the discipline, and so it's very hard. There's for many of these problems, many different methods, and there's people have experience about which things work well, but there's very few formal results that particular things are guaranteed to work well under particular conditions. And so the setting is often one where there's fairly large data sets, and that can take the form of having many observations, many units, but it can also take the form of having many predictors, covariates, regressors, features. And so scalability of a lot of these methods is very important. There's a lot of cases where we would actually know what to do very well if computational issues were not a problem, but these methods are intended to be used automatically with very little human intervention on very large data sets. Another feature is that often causality is de-emphasized. It's very explicitly about prediction, and the labels are often irrelevant. And that's actually a very important thing, because it makes, but once you de-emphasize causality and focus on prediction, cross-validation, out-of-sample cross-validation is going to be much easier than in settings where causality is a big issue. Final thing that makes part of this literature hard to parse sometimes is that there's a lot of new terms for things that we're very familiar with. Here, there's a lot of talk about training models rather than estimating them. Hypotheses are used in a very different way than we typically do in statistics. And so just reading the literature is often a little painful to try to figure out what people mean in familiar terms. But so I want to stress three key components in these first 2 hours of these lectures. One is that there's a big emphasis on out-of-sample cross-validation. So rather than figuring out the theoretical properties of these methods the way we typically do, and the way they've been well established for things like maximum likelihood estimation or GMM estimation, people assess the properties by looking out of sample. And so typically that takes the form of cross-validation exercises where the data is split into a training sample and a test sample. The model is estimated or trained on the training sample, and then it's assessed, its performance is assessed or compared to that of other methods on this test sample, so that there's no possibility of overfitting leading to the favoring of very large models. And so, as I said before, and as Susan will illustrate in later this afternoon, that creates a lot of problems in cases where we're interested in causal effects, because unlike prediction problems, we generally don't have unbiased estimates of what the truth is in models for causal effects. Second theme is that of regularization, and so here we'll tend to look at models that can be very big, and then there needs to be special care taken to avoid overfitting. And so rather than choosing models in a class to optimize the fit of the model, there's typically going to be some regularization, some penalty to avoid overfitting. And there's going to be two questions, sort of how you choose the form of the regularization, as well as the amount of the regularization. Second part is sort of relatively easy. Typically that's done through cross-validation, where repeatedly the data is split into two to figure out what the optimal amount of regularization is. The form of the regularization is much harder, and there those are typically chosen on partly on theoretical grounds and on more sort of using more ad hoc methods, and often different ways of choosing the form of the regularization lead to very different algorithms with sometimes surprisingly different properties. But this is an area where the lack of structure can make things very difficult. Often, you know that you would like to be very flexible in the form of the regularization, but there's only a limited amount you can do in terms of actually implementing on that. And so the third theme is scalability. That we want these methods, in the literature, we want these methods to be able to handle very large amounts of data and work well so automatically without much human intervention. And so one key aspect is that typically we want to use methods that parallelize rather than to speed up the computation. And so, for example, if you think of methods used in programming evaluation, like matching methods, they can be very computationally intensive. And so there's been a lot of work trying to find methods that do almost as well theoretically, but that scale up much better. Locally sensitive hashing is one of the key ideas there. So in terms of the supervised learning that I'm going to spend all of the first lecture on, there's sort of two problems that I want to focus on. I'm just going to mention the first really and then focus on the second one. First is classification. The idea there is we have a number of observations on pairs of two variables, y and x. X is an element of an unordered set of integers. And what we're trying to do is find a function that will map for any value of x, the original set of observations into into one of these categories. So given the data for a new value of x, we want to assign them to one of these new categories. We don't necessarily, and so traditionally we might have, in econometrics, we might have done this using logistic regression models where we model the probability of belonging to one of these categories. Here, that's not always the goal. Often, we don't actually need the probabilities. We just want to get one of these integers out of the algorithm. And some of these algorithms never come up with a probability there. So what we want to do there is just assign new observations to one of these categories. And big successes there in the machine learning literature has been the automatic reading of zip codes. So there, the idea is you see someone writing something, and you want to classify it into one of 10 categories, namely digits from 0 to 9. And there's no interest there in causality beyond well, in fact, I used an example that once, and then one of my statistics friends said, "Wow, in fact, now when he wrote envelopes, he actually did that being aware of the fact that these things were going to be read by machines, and so he knew to make sure that they would actually be readable to a machine rather than readable by humans." But in principle, there it's a pure prediction problem. There's obviously modern versions of that are face recognition that is being used very widely at places like Facebook. But so what I want to spend most of the time on is a problem that's actually very familiar from the economic and econometric literature, which essentially which we used to refer to as nonparametric regression. Again, we have n observations on the pair y and x. Now y is maybe a continuous variable or discrete, but we're trying to predict, we're trying to come up with the expected value for y given x. And in fact, in these lectures in 2007, we did talk briefly about nonparametric regression. And what people typically used in econometrics at that time was kernel regression. And it had a lot of very nice features. It was easy to establish asymptotic properties for these methods, and they were fairly easy to implement. But it was also very widely understood that this didn't really work very well with lots of regressors. You could do this, and you could make pretty plots if you had one or two regressors, but nobody really ever tried to do this with 10 regressors, let alone with thousands of regressors. And what we're trying to do here is looking at methods where you could think of implementing this with thousands of regressors or features. And so partly the price we'll pay is that for a lot of these methods, there's actually not going to be asymptotic results. In fact, in a lot of cases, it's clear that there's not going to be asymptotic normality. In some cases, there's been suggestions that asymptotic normality and general large sample properties may hold, in particular for random forests. But that's not been a main topic in this literature. So now let me get to the main part of this first lecture. And let me start just with a look at linear regression. So the way we typically do that in econometrics, teach it in the econometrics courses, we have a relatively small number of covariates, we model them, we model the regression function as linear, and those covariates, we estimate the model by least squares. And we teach the undergraduates and graduate students that these estimators have very good properties, and that therefore they should be widely used. Now, of course, these optimality properties are actually very limited. We know that in general, OLS is not even admissible, but in practice, it works very well with, for small values of k, when we have relatively few covariates. The question is what to do when we have many covariates. And again, we want to implement this with thousands of regressors, sometimes millions of regressors, and a very large number of observations. And in some cases, there may actually be more covariates, more predictors than we have observations. And so clearly in that case, we can't do OLS. Now, many years ago, when I sit in the econometric seminars at Harvard, I remember the great Sri Gulijas saying that we should never trust OLS with more than 5 regressors. And so the context was really that he thought you shouldn't really look at those problems. It didn't really, there was nothing that was really going to work well if you had lots of regressors. And now here, that is exactly the focus of a large part of this literature. And so what we need to do is find some way of regularizing these problems, of smoothing them, of shrinking them towards particular values, so that we don't run into the invertibility problems or the poor properties of OLS with many covariates. And so here's another quote. I'm going to give a couple of these quotes, and you can kind of decide whether that's to hide my ignorance here or to just show that I've read this literature. But so Vapnik was come up with the support vector machines methods. Wrote that regularization theory was one of the first signs of the existence of intelligent inference. You can already see from here that he's not necessarily a very generous person. I think there was a lot of statistics that reflected intelligent inference. And so when I talked to a friend of mine about this, who knew Vapnik, he said someone once asked Vapnik why he was being so abrasive. And Vapnik's comment was that 100 years from now, they weren't going to remember whether he was nice or not, but they were going to remember his work. So, but so what do we do? How do we regularize these problems? So I'm not really sure in Vapnik's case that's completely right, but 30 years is probably exactly. So he could have been an economist. But so let's now look at regression, at regularization regression. So there's sort of 3 things we can do. One is to shrink estimates continuously towards 0. So I'm still going to do this in the least squares context. So we could do OLS, but we may have a large number of regressors, so we don't think it works very well, or we may have so many that we can't actually do least squares directly. So we could just shrink all the estimates towards some common value, and typically that would be 0. Or we could limit the number of non-zero estimates. And that's sort of a big idea, the notion of a sparse representation, that we're going to select some of the covariates to enter into the regression and drop others. Of course, we always do that informally by just choosing which regressors we include. But here, I'm going to talk about systematic ways of doing that. And so here's, again, is a quote from the highly recommended book by Hastie, Tibshirani, and Wainwright, where they refer to this as the sparsity principle. And they say, in the end, you should use methods that do well in sparse problems, so where, in fact, there are a lot of zeros, a lot of coefficients that are very close to 0. Because if in fact the problem is sparse, these methods are going to do well, which seems plausible. But the other part of the argument is very interesting. Say, because no procedure is going to do well in dense problems. So this is very much, and I've been accused of that in my own work, but so this is very much a case of looking for your keys where the light is. They say, well, problems that are dense, where a lot of these coefficients are different from 0, and we have no idea, we have no structure on them, we're never going to do well. If we have 1,000 observations and 800 regressors, we cannot figure out these coefficients if you have no structure on there. And so just don't think about those problems. Just try to deal with the case where you know there's only a couple that matter and the others don't matter. And in the discussion here in the other book by Friedman, Hasty, Tibshirani, they discuss this in more detail, and they argue that there's actually deeper reasons for doing this that I'm not sure that are entirely convincing. But this is a huge issue. The idea of looking for these representations where you try to select some submodels that zero out a bunch of the coefficients is a very important concept. And then we can combine these things where we do some shrinking towards zero and dropping some coefficients directly. So the first method that fits into this framework is just doing subset selection. You could try to look for the set of covariates that gives you the best approximation to the regression function by limiting the number of non-zero coefficients or putting a penalty on the number of non-zero coefficients, where the beta naught is just the L0 norm, where you just count the number of non-zero coefficients. Trouble with this is it's very hard computationally. In principle, you would need to look over all subsets, and so if you want to want to allow for 50 covariates and you have 1 million covariates, that would be a very hard problem. You can't deal with it computationally, even though it may be better in principle than some of these other methods. This is just not scalable. Second method that goes back a long way is ridge regression, where you modify the OLS estimator by putting in the denominator there, where you add into the denominator lambda times the identity matrix. And I should actually add, I should have said this before, typically in these methods, we first normalize all the covariates to have mean 0 and variance 1, so they're on the same scale. Otherwise, obviously, adding lambda times the identity matrix wouldn't be a very natural thing to do. But now, once we've done that, this is a somewhat natural thing to do. We ensure that the matrix in the denominator now is invertible, and we end up shrinking all the estimates towards 0. It has a very nice interpretation, too, from a Bayesian perspective. If you had a prior distribution for beta that was normal, and if the distribution of epsilon was normal, then for some values of lambda, the ridge regression estimator would be the posterior mean. The posterior distribution would in fact be normal, and this would give you the posterior mean. And here, all the estimates are shrunk smoothly towards 0. If they were all uncorrelated, we would in fact shrink them all by the same factor, 1 over 1 plus lambda. In general, it's a little bit more complicated, but it's sort of a very familiar thing to do. And it scales up reasonably well, other than at the point where you have so many covariates that you can't really invert this matrix very easily, which is in general not going to be a sparse matrix. And so the matrix inversion at some point is going to make this hard. If you do this for 1 billion observations, you would have a billion by billion matrix, and that's hard to invert. And so now, what is in between these things, and which is has become incredibly important in the statistics literature and in the machine learning literature. So here's a quote from Andrew Gellman's blog, kind of where he sort of talked a bit about his early unease with lasso and how he became convinced that it's a very important thing. And so what it stands for actually is least absolute selection and shrinkage operator. The Stanford guys are very good at coming up with labels for their methods, as we'll see in a bit. But so what they, and this goes back to Tibshirani 96, what he suggests is minimizing sum of squares, but then adding a penalty term that, in contrast to the subset selection where it was the L0 norm, or the ridge regression where there was the L2 norm, now it's the L1 norm. So we sum the absolute values for the betas, and it turns out that has very interesting features that make it sort of both computationally easy as well as make it have a nice interpretation. So the comparison is to ridge, where we use this L2 norm, or the subset selection, where we use the L0 norm. so what Rich is going to do, let me see, I don't have a pointer here, I think, or at least. So here, it shows you how the three different methods shrink OLS estimates towards zero. So we start off with the least squares estimates. We just have a single regressor here. The Rich would just multiply the coefficient by some constant between 0 and 1. The subset selection would set the coefficient equal to 0 up to some point and then go with the OLS coefficient. And Lasso does something in between, where up to a point it sets the coefficient equal to 0, and then it goes up linearly, but it stays below the least squares coefficient. So this is Rich, this is subset selection, and this one is Lasso. And so one thing to take away from this is that compared to Rich, for very large values of the coefficients, there's going to be a big difference between Rich and on the one hand and Lasso and subset selection on the other hand. So in cases where there's some regressors that you think are very important, Rich is not going to do very well because it's going to shrink the large coefficients much more than Lasso or subset selection would. And that's that has a lot of the intuition for when Lasso might be doing better than Rich in practice. Now, so here's another plot kind of to illustrate why with Lasso we occasionally may end up with exact zeros and why we never end up there with Rich. So here, if you look at Rich regression, if we have the OLS estimates, one way of thinking about the problem is that we shrink these OLS estimates towards 0. And so given an amount of shrinkage, we want to have estimates that are inside this circle. We look for the closest value to the OLS estimates that is within this circle. And that's always going to be, or in general, that's going to be somewhere away from the points where one of these coefficients is equal to 0. When we do the same thing with Lasso, restricting the coefficient means we're restricting them to these rotated squares. And now the closest value to the OLS coefficients may be on one of these edges, but it could also, but in many cases, it's going to be on one of these, on one of the axes where you set some of the coefficients exactly equal to 0. So compared to Rich, Lasso is going to zero out some of the coefficients and shrink the others a little bit towards 0, but it could end up with all coefficients non-zero. Now, there's sort of lots of other ways of doing that have some of these same properties. And so partly want to mention these not because they're all that interesting in their own right, but it sort of shows you how special Lasso is in some of its property. There's a method developed by Efron called least angle regression, or LARS. There's sort of a stage-wise procedure that's a little bit more like stepwise regression, but it provides an algorithm for actually calculating the Lasso coefficients as a function of the penalty parameter. And so that is very helpful in terms of implementing these methods, because it shows you which coefficients enter into the regression function as you relax the penalty parameter. Then there's another closely related method called the Danzig selector, named in honor of Danzig from linear programming, because the actual computational methods for doing this involve a lot of linear programming by Candace and Tao. Partly mentioning this because Candace is our neighbor at Stanford, living 100 yards from where we do. That's again a very clever method, and in principle, theoretically, you could expect it to do very well, and very much like Lasso. It turns out in practice it doesn't work very well, and it turns out that the particular way in which Lasso looks at the estimates and does the regularization is just works out incredibly well. here's just kind of a general slide that this is actually one of the few methods that has made some inroads into econometrics. There's been a lot of work by Baloni, Chernosikov, and Hansen. The Journal of Economic Perspectives paper gives a lot of references to that literature. And so what is special here? It's there's a couple of features. One is the fact that it shrinks some of these coefficients exactly to zero, makes it much more interpretable. In the end, if you do this, say with a couple of hundred regressors, in many cases you would just end up with 5 or 10, and you can actually look at which ones matter. It also scales up incredibly well, even compared to Rich, where there's actually an analytic solution for the estimator. If you have many observations, inverting the covariance many covariates, inverting the covariance matrix can be a problem. So conceptually, it is also interesting to think why it might work well relative to Lasso. And there, this Baton Sparsity issue is very important. In many cases, so if you actually look at Tibshirani's original 96 paper, he kind of talks about the fact that if you think that there's many covariates and they all have similar sized coefficients, then Ridge is a very natural thing, or in general, putting a prior on these coefficients with common mean and some variance is a very natural way to go. But where Lasso is likely to do well is in cases where the covariates are very different, where you think that some of these covariates, but you need not necessarily know in advance, where some of these covariates matter much more than the others. At that point, the fact that Ridge shrinks the large coefficients much more than Lasso becomes a big issue. And so, because it's very hard to think beforehand about what the distribution of these coefficients in settings with a large number of covariates looks like. But I think it's certainly plausible that there are some coefficients that matter a lot. If you kind of think about trying to predict individuals' behavior, it's likely that some features, some characteristics of these individuals matter much more than others, rather than that it's all a mush and they're all somewhat similar sized. But again, that's not really a theoretical argument, and it's certainly the case if you think about this from a Bayesian perspective, that if you think the distribution of these covariates is more like a normal than like a Laplace distribution, Ridge should do better than Lasso. Focusing on the covariate selection the way Lasso does have some awkward aspects. Sometimes we think about super efficient estimators where we try to estimate a mean and estimate it by 0 if the average is close to 0, and by the sample average if the average is far away from 0. And you can show that estimator is super efficient in the sense that it always does as well as the mean in large samples, but it does much better than the mean if the true population mean is close to 0. And so Lasso has the same feature. It kind of shrinks these estimates towards 0, and it does very well if these estimates are very close to 0. But the same way, we don't really ever use these super efficient estimators for the mean because we think they do very poorly when the population mean is close to 0 but not identical to 0. Lasso is not going to do well if a lot of these coefficients are close to 0 but a little too far away from 0 for 0 to give you good approximation. In that case, Ridge would do much better. Another aspect is that the nature of the penalty term means it's going to be unstable when we have very highly correlated regressors. In particular, if you put in 2 copies of the same regressor, Ridge would have no problem with that. It would shrink both of them to about approximately half the magnitude of the sum of these coefficients. But Lasso would be indifferent between many values, and as a result, it tends to be unstable if you have a lot of very highly correlated regressors. Another attractive feature of Lasso is that it has an interpretation in terms of a Bayesian analysis. If you start with a prior distribution for the betas that has a Laplace distribution, and you focus on the posterior mode, then you would get the lasso estimates. Because from a Bayesian perspective, using the posterior mode is a somewhat odd thing, but that is key here to getting the sparsity property, that a lot of these estimates are exactly equal to 0. What is more interesting is the choice of the prior, where I think in a lot of cases a normal prior would probably be less reasonable than a Laplace prior if you want to allow for some of these coefficients to actually be large. Another Bayesian method that is useful to kind of to put this in perspective is what is referred to as a spike and slab prior, where you could specify a prior distribution that puts point mass at 0 and then has a continuous distribution for non-zero values, say a normal distribution or even a Laplace distribution. That would be very much in line with lasso, but it doesn't scale up as well as lasso. Let me make a couple of comments on how you actually implement things, and I don't do this with the idea that based on this very short discussion you would actually directly be able to implement this. But I want to point out some of the issues that come up when you actually implement this. There's a lot of very good software available for these methods. If you go to Tibshirani's homepage, there's links to all of them, but it's been implemented in MATLAB. There's a lot of R program software available, but there's a bunch of choices to be made still in these methods that matter, and certainly if you want to be able to replicate results based on different software. So the idea is to minimize the sum of squared deviations using this the penalty, this L1 penalty term. We can rewrite that as minimizing sum of squares subject to the sum of the coefficients being less than some constant. And often people scale that by the sum of the least squares coefficients, so you get this scaling coefficient to be between 0 and 1. So then the question is how to choose the amount of regularization, either in terms of lambda or t. And you could do that both ways, so it may make a difference whether you regularize on lambda or on t. What we typically do there, what's typically done in this literature, is using cross-validation, typically for no particular reason other than it's sort of nice to have consensus numbers there. People do 10-fold cross-validation. So we divide the sample into 10 cross-validation samples. For each of those 10 samples, we first estimate the model for a given value of lambda on the remainder, on the 90% of the data. Then we calculate the sum of square deviations for that value of lambda. We sum up over all the cross-validation samples, and in principle, that's something we could minimize over the cross-validation parameter. That's not quite what is typically done. Tibshirani and his co-authors recommend actually using a smaller value, so using a larger value for lambda, doing more regularization than you would get out of simply minimizing the cross-validation mean squared error. So what they do is they calculate standard error over the cross-validation samples and then choose the largest lambda that is reasonably close to minimizing the cross-validation error, where the reasonably close is measured in terms of the standard error. And so this is one of these places where there's a lot of ad hoc decisions in the end going into this. Why exactly this is the right way of doing it is not clear, but the experience of suggests that that's a reasonable way to go. One final point on the lasso is what is referred to as the oracle property, and that's reminiscent of the super efficient estimation discussion a couple of minutes ago. If in fact the true model is sparse, and obviously in social science applications or in any application that's really very unlikely, but if it were true that the model is sparse, and if it's true that the number of non-zero coefficients is relatively small relative to the number of observations, then ultimately you can do inference. You can calculate, construct confidence intervals based on the lasso estimates, ignoring the fact that you selected all these zero coefficients. You can just do OLS on the coefficients, on the regressors that are selected, and the regular OLS standard errors give you valid confidence intervals. Because in practice, that is not always going to give you a good approximation. In the end, if you start with 1,000 covariates and you get it down to 10, ignoring the fact that you spend a fair amount of data on getting rid of these 990 covariates, can't always work. But at least in principle, it suggests it may not always give you a bad approximation. Just kind of to show you how this performs relative to least squares. So I took some data, actually, this is from a data set that I've used many times, that's originally from Lalonde. Here I have data on earnings and a bunch of, and 8 covariates, some binary, some continuous. And I created additional covariates by just including all third order interactions. So I had 121 covariates. I used a training sample of about 8,000 observations and a test sample of about 8,000 observations. And I compared OLS with all 121 covariates versus Lasso, which selected 15 out of the 121 covariates. And the root mean squared error in the OLS sample is just is about twice the size of what it is for Lasso. The OLS can't really deal with that many covariates. You can sort of see that here, where there's a scatter plot of the OLS estimate, OLS predicted values for all the observations versus the Lasso predicted values. What you see is that occasionally the OLS estimates are just very wild. Even though none of the individual coefficients was particularly badly estimated, occasionally the predictions based on OLS would just be very, very far off. One modification of Lasso that is fairly popular is what is referred to as elastic nets. And that's a way of sort of combining the features of ridge regression and Lasso regression. The idea is to look at a penalty term that's a convex combination of L1 penalty and a L2 penalty with weights alpha and 1 minus alpha, and then do overall shrinkage on that combined penalty term. And so if you actually fix alpha at 0, you would be back doing Lasso. If you fix alpha at 1, you would be back doing ridge regression. But now you have something that could, in principle, deal with settings where Lasso does well, as well as settings where ridge does well. Here you run into these general problems that, in principle, you can make the regularization very complicated, but it becomes harder to actually implement it in practice. You can't really use test samples to optimize both over alpha and lambda in a very fine way. And so what people do in practice there is just choosing a couple of possible values for alpha and then only choosing lambdas through cross-validation. So, for example, take 5 values of alpha and optimize over those as well as lambda, rather than try to do both alpha and lambda continuously, which would make the problem unstable. Okay, so that finishes the part on Lasso, on linear regression type methods. And so let me just kind of summarize that with saying that, again, giving a quote from Gelman. He wrote on his blog somewhere that Lasso is the new OLS. And so he viewed it as something that you should just do routinely, the same way we do OLS now. We know that OLS doesn't really work very well in a lot of cases where we have a lot of covariates. Lasso is still going to do very well if you have few covariates, because the shrinkage is going to matter very little. And so as a matter of routine, he suggests that people should really be using Lasso-type shrinkage rather than conventional OLS, with the idea that you're not really doing much harm if OLS works well. But if there's a difference between the two, it's very likely that lasso is going to give you more reliable results. And so when Gelman wrote this, he sort of was partly arguing that originally he didn't really think that much of lasso, but he became convinced by the subsequent literature. So this is a fairly unbiased opinion there. So the second set of methods I want to look at is regression trees. And so there, the problem in principle is the same one. We're trying to estimate a regression function non-parametrically in a flexible way. But regression trees come at this from a very different perspective. The idea is to partition the covariate space into subspaces and then estimate the regression function within each of these subspaces as the average outcome for units with covariance values in that subspace. Now, later actually, and I'm not going to go into details there, but in principle you could do lots of other things other than using the average outcome as an estimate within that subspace. You could, within these subspaces, estimate sort of a parsimonious linear model or do anything else. But the idea is to partition the covariate space and do separate things in these separate subspaces. And the question is how to come up with a computationally feasible and sensible way of partitioning the covariate space in cases where we may have many covariates and they may be binary, they may be continuous, so we can't directly look over all possible subspaces. And so in some sense this is a little bit similar to doing nearest neighbor estimation, where you also you just average outcomes for units very close to the place where you're trying to estimate the regression function. But here this is doing it in an adaptive way, where some of these subspaces may be very large if in fact there's little evidence that the regression function varies a lot. And it's going to divide the spaces into small subspaces if there's evidence that there's a lot of variation in the regression function. So the starting point is just taking the whole covariate space and estimating the regression function as the sample average of the outcomes. Then the objective function is the sum of squared deviations from the estimated regression function. So in this case, the sum of squared deviations from the mean. Then for each of the capital K covariates, for each value in the support of each of these covariates, you could imagine splitting the data. So if we split it on covariate K for threshold T, we would split the sample into two subsamples depending on whether the covariate for unit I, for covariate K, is less than or equal to T or greater than T. We then calculate the average in these two subsamples, and we look at and then obviously we've reduced the sum of squared deviations from the regression function. Because now we just calculate the average within these subsamples. But if we split it on a different covariate, we might do better, or if we split it at a different threshold. And so the idea behind the tree algorithm is to look for the covariate and the threshold that minimizes the sum of squared deviations after the split. And so you pick that particular combination of covariate and threshold and split the sample in two subsamples, and then you do that repeatedly. You keep doing that. Each time now, in addition to choosing between covariates and thresholds, you also choose between different subspaces to split, but you split the leaf, the subspace, and the covariate and the threshold that gives you the most improvement in the sum of squared residuals. And each time you do that, you're going to reduce that sum of squared residuals. And so we again need to impose some regularization. And the one that is typically used is to add a penalty term that is proportional to the number of subspaces, to the number of leaves in the tree. And the result here is going to be that you have what is called a tree. You have a step function that estimates the regression function as a sample average within each of a bunch of subspaces, and we're trying to come up with the optimal set of subspaces for getting the tree there. Now, to implement that, we again need to choose the amount of regularization, the penalty term lambda, and the conventional thing to do in this literature is to do cross-validation. So again, we divide the sample into, say, 10 cross-validation samples. Each time we estimate the tree using all the other data other than the B cross-validation sample. We do that for all values of lambda. Then for all values of lambda, we sum up the squared residuals over the cross-validation sample, and then we choose the lambda that minimizes this criterion over all values of the regularization parameter. Here, unlike in the Lasso case, most of the software focuses directly on minimizing the sum of squared residuals, rather than have the standard error thing that was suggested in the Lasso case. But sort of that's partly because I don't think anybody has particularly looked at that. It's sort of hard to argue that one way would be systematically better than doing it some other way. But the conventional thing in the tree literature is to focus on criteria of this type.